So for part two, we're going to be diving into the swing phase, which has three main components here. The stance phase for the reference limb has been completed, and now it's into this open kinematic chain position where it's advancing, getting ready to bear weight, but not quite yet. And the swing phase is going to have the early swing phase, then the mid swing phase, and then you can imagine the terminal swing phase. So we know that the swing phase does compensate for 40% of the gait cycle. And there's this initial swing phase. So this swinging is going to occur underneath the center of mass, underneath the body, before it starts to get further into the body. So it's going to start a little distal and then it's going to go towards the center of mass. Because in the mid-swing phase, you could see that the reference extremity is basically under the center of mass. It may be a little, considered a little posterior at this point, but the knee is flexed and the ankle is in this neutral position. So it's basically in line with the center of mass. So this is when the knee is in typically the most amount of flexion. And if it's not in a lot of flexion, the toes can drag on the ground or hit the ground, and you could trip over things. And this could be a problem for falling and so forth. So this is really the end of the acceleration, beginning to decelerate at this point. And then the ends when the tibia is perpendicular to the foot. And then we have, going from mid-swing, we go to terminal swing or late swing, depending on the terminology. So this is the final part before this reference limb is about to hit the ground. Now the center of mass for the lower extremity is going to shift more anterior. So the final phase is going to involve deceleration. So before this heel strikes the ground, or before you have that initial contact for the stance phase, it's got to decelerate, or we could say have a negative acceleration before that hits the ground. So you're going to start with acceleration and you're going to go to deceleration as it hits the ground, basically. And here's a representation of the entire swing phase. So you can see initial swing, mid-swing, terminal swing. So if we were to tie it all together, this is a great slide to know. I would print this out or put asterisks and highlight this. There's a lot of information contained in this slide. And if you look at this, it's not really labeled as clearly, but this right lower extremity is going to be the reference limb. So it's going to take you for the right lower extremity through the entire stance phase. That's going to be the first 60%. And then the remaining swing phase. So until that right lower extremity gets contact a second time, and so this, at this point right here, it's going to start another 60% of the stance phase. So this will be your second cycle over here, but this is your complete cycle. So look through this, make sure that this entire slide makes sense to you. There's going to be a lot of terminology associated with this. Here's a summary slide to cross-reference with the last slide if you're looking for some more words to describe everything. This will be good. As you're learning this, I really encourage you to have this on a note card or a piece of paper and walk in slow motion as these different phases happen. I think it helps to do that. If you want to stand in front of a mirror or something like that, you can do that as well, or at least to watch someone else walking in slow motion, a partner or someone else in class, but to say these words out loud as each one happens during a slow motion gait sometimes can be helpful to learn this material. Okay, so that's the point of the mannequin challenge, is to walk in slow motion and just practice these different things. Or you can watch a video and pause the video or watch it in slow motion as you do this. To give some other words associated with this, there's really two types of variables. We have time or temporal variables, such as how long is someone in stance phase, how long are they in swing phase, how long between their steps, what's their cadence, which is the number of steps per minute, what are the number of seconds, and so forth. And then you're also looking at your distance variables. How many centimeters is their stride? How many centimeters or inches is their step? How wide is their base of support? How many degrees are they toed out? If our toes are facing completely forward, they'd both be at 12 o'clock, but is the right foot at 1 o'clock and the left foot at 11 o'clock? How much as a percentage is one limb compared to the other limb in terms of the stride length for each? How far does someone walk? Those are distance variables versus time variables. And that seems to make sense probably. In terms of support time, this is another percentage to know and to be aware of. In terms of stance, we're looking at single support time, which is 80% of the time, compared to double support time, which is 20% of the time. So double support, double, 2 legs. How much time is spent with both feet on the ground during one gait cycle? And then you can imagine that this decreases as the speed of walking increases. So it's that inverse relationship. But if this helps you to visualize that, it would be good. You can imagine that as you get elderly, you tend to have an increased double support time. So as you start to take shorter strides, you start to have more support because you're in double support more of the time. And here's a visual of that as well. So it's just repeating the information in a visual format. So here's your single support during stance phase, and then here's your swing phase. So as you can imagine, as we get older, we might want to decrease that swing phase, take shorter steps to increase this stance phase with double and double. So the cadence and velocity, these are other terminologies that are important to know. Cadence is the number of steps taken in a second or a minute. Typically, we do refer to this as minute. So if I said someone had a cadence of 60, that means they would be taking 60 steps per minute. So as the cadence increases, the number of steps taken also increases. And you can imagine the time during each stance or swing phase would decrease. Because if you're getting 120 steps per minute, you're getting a lot more steps in the same amount of time. So it basically reduce the time in stance and swing by 50%. Versus the velocity is the overall speed of ambulation. This goes back to, I think it's the first week of kinesiology. We talked about how this is typically measured in the metric system in meters per second. It could be measured in feet per second, but most standardized outcome measures use meters per second. So if we walk, 2 meters per second, that would be half as fast as if we walk 4 meters per second. So we generally look at this. Some normal values for this tend to be 1.2 to 1.4 meters per second. That's a commonly cited normal range, 1.2 to 1.4 meters per second. And how do we measure that? So typically we have an area marked, and usually 10 meters is easy because it's easy for us to do the math. With that, we take the time and we divide that out. So usually we give someone a walking start for this. We don't usually start at 0 at still and then have the timer start and have them start walking at the same time, because we give them time to build up their speed to a normal walking speed. So while someone's walking, we want to know what their gait speed is, or their gait velocity is, during the normal walking time, and then they can decelerate. So this is a commonly cited way to measure this. And then in terms of efficiency for our system, or energy expenditure, we talk about energy as a form of work, internal or external work. We're talking more about internal work as it's related to caloric expenditure. Here, there is basically an ideal or an efficient walking speed. So our bodies are relatively inefficient at a slow walking speed. It requires more energy for us to do that. And then there is this between 60 and 120, we're relatively efficient. And then as we start to walk faster, it actually requires more effort, which is why a lot of individuals at this point, if you're walking really fast, and you can imagine 140 meters per minute, you start to really jog or run at this point. So just understand that there is that balance and there's this ideal walking speed within here. Going to the distance variables, we're looking at this slide on step length. So you can see the right step length and the left step length. So if you look at the heel of your right foot and measure that distance until the heel of the left foot, or where that would remain in contact. So not the diagonal distance, but just a straight line from A to B here. That would be the left step length. I want to make a point. It's not from where the left foot initially contacts until where it contacts again. That would be the stride length. We're talking about the step length from left to right. So this is the step length here on this slide, not to be confused with the stride length here. So the stride length would be from when the right foot contacts the ground until when the right foot contacts the ground again. That would be the right stride. The left stride isn't really pictured here, but it's when the left heel or foot would contact compared to when the left foot or heel contacts again. So stride duration and gait cycle duration would be synonymous terms. 1 stride per second. So that's step length and stride length. So you can see the stride length is always going to be greater than the step length. And here's another variation of that, putting the terminologies together so you could see, for the reference limb, so you could see the step length. Here's the right foot making contact, and here's the left foot making contact. What's the distance between the right and left foot contact points? That's the step length. And then the stride length would be, here's when the right foot makes contact, here's when the right foot makes contact again. The total distance would be the stride length there. So that's looking at it in this view. But we also have a medial to lateral view about the step width. So you can see here, this is the measure of width at the base of support. So if you look there to there, what is the distance between when that left foot contacts to when the right foot contacts? And if you think about this, there's a range here of 1 to 5 inches. The mean is 3.5 inches. But the greater the number here, let's say you're closer to 5 inches or 6 inches, the greater the number here of the step width, the greater your base of support is. The smaller the number, the lower the base of support is. So you can imagine if someone's walking a tightrope, there's a very small step width. Essentially, there's a 0 for the step width. And as we walk, let's say you're walking on ice, if you're walking on ice or something slippery, you might take a wider step width because you want to increase your base of support and lower your center of mass. So if you watch elderly individuals or small children walk, you'll notice that traditionally they have a really wide step width, or I could say an increased step width, because they want to increase their stability. And that's going to also decrease their center of mass to make the center of mass closer to the floor, which adds for stability that way. So that's your step width. Very similar to your toe out angle. This also increases your overall base of support. Once again, if you watch elderly people, they might start to toe out more. That could be because of some hip capsular deficits, lacking internal rotation. But it also could be because they're trying to increase that toe out angle. From the foot and ankle unit, you may remember that we look at this as the too many toes sign. So if you're looking at someone from the posterior view and you could see their toes from behind, that's showing external rotation of the foot or external rotation of the tibia. A toeing out angle is something we're looking for. So if this was, I like to describe this, if this were 12 o'clock, if it's going towards, if the toes would be pointing towards 3 o'clock as an extreme, that would be a 90-degree toe out angle, which I don't think we'd see. But if it's going more from 12 o'clock to 1 o'clock, that might be a 30-degree toe out angle. It's going to depend. That's an extreme. You could see traditionally we're looking about a 7-degree toe out angle. And this is something where if you walk in the sand and you look at your footprints and you can actually start to notice, well, how far am I toeing out? Some people will have a 0-degree. They'll be completely at 12 o'clock the entire time, and others seem to vary that. Then in terms of whether or not this changes with your walking speed, generally if you think about walking faster, it's more challenging, so you need more stability. So we typically have an increased toe out with increased walking speed. However, this should be monitored, and it could be an individualized assessment to determine what happens. So walk at a normal speed, now walk fast or do more of a brisk walk like you're in a hurry to go somewhere, and see if you notice with yourself or with the patient what happens to their toe out angle. This is really easy to look at on a treadmill. It's harder to look at on a flat surface because they're getting either closer to you or further to you at a fast speed. But if you were to look at them from behind or from the front of them on a treadmill, and then you could set the treadmill speed. Let's say you set the treadmill speed at 2 miles per hour and watch them, and then increase the treadmill speed to 3 or 3.5 miles per hour. Which is a pretty good pace. And then you can see how does that angle change. So if you're going to the gym or walking outside, try this a little bit and see if you notice a change in your toe out angle with your speed. Some more kinematic terms here associated with this. Trajectories are important to know, and there's a lot of technology we can use that will measure these types of joint angles, especially if we have biomechanical markers. One of the programs we looked at for the knee PowerPoint was that Dartfish program where you have markers on an individual and then they walk, and then you can use the computer program to measure the angles with that, and there's some cool things you could do with technology and that, and we will look at a little bit of this terminology during the Gait lab portion for the final week. One of the things we are looking at as it relates to the center of mass and the head position, so you can see this is showing as you walk and as you go from single and double limb support, you have a small vertical displacement of the head as your head goes up and down. So you can imagine in that mid-stance phase, you're in a taller position, and then as you're in that double limb support, you're in the lowest position. So it follows this waveform, this sinusoidal waveform, and it may go up and down about 5 centimeters. Obviously, the taller you are, the more this will vary. And so if you're looking at a smaller child, it may only fluctuate 2 or 3 centimeters, but the average adult is going to have about a 4 to 5 centimeter variation, displacement, rise and fall, according to which phase of the gait cycle that they're in. And then laterally, we know we don't just walk in a straight line. There is a little bit of variation, medial and lateral. So there's this lateral displacement as well. And this also tends to be around 5 centimeters, 4 to 5 centimeters, right around here. So 5 centimeters is a good number to know for vertical displacement and lateral displacement, and there's a little variation with that. So at that point, let's wrap up this part, and then we'll finish it up with part 3 of this PowerPoint.